research in the 90s. There are libraries which are written in Haskell for recursion schemes, and my colleagues written a project which is called Matryoshka, which ports those Haskell libraries into Scala. And this is what we're going to see in a minute. So I'll just skip the introduction because we don't have time for it. But basically, there's a paper which was written by Eric Meyer. You probably know Eric Meyer because he's this really crazy dude with those crazy, like, colorful T-shirts. If you've ever seen, like, Haskell course on some platforms out there, that's this guy. And he wrote this paper about recursion schemes in 1995. And what we do is we utilize those recursion schemes he described and use them in our project. So I know it sounds all weird, so without further ado, let me tell you what this talk is really about. So this talk is about recursion. And recursion basically sucks. It's a super complex idea that always provides errors in our programs. And what we'd like to have is something that would allow us to at least remove that complexity someplace else. Think of go-to. Go-to, a keyword in some languages like Fortran. Dijkstra wrote a paper in the 60s, a paper which is 2 pages long, which is called Go-to Consider Harmful. And he never really said that go-to should be deleted from our programming languages. He only said that go-to should not be visible in higher-level languages. So Scala and Java, we have go-to in the bytecode. Bytecode has a go-to element within the language. We just don't see it in Scala or in Java, right? We have our while loop, for loop, and all that. We use high-level abstraction, but underneath, it still is using go-to. So recursion schemes, if you want to build some kind of metaphor in your head, recursion schemes are doing the same thing, but for recursion. We're still doing recursive calls, but we don't have them in our project. We have some lower level machinery that will actually do that for us. So without further ado, I don't know how much time do I have. Is it like 30 minutes or 40? Do you guys know? 40. All right, awesome. So just a quick example here that recursion structures. So when I say a recursion structure, it's like any structure that is defined inductively, meaning like the easiest example would be list, right? If you have lists in Scala, you have either cons, which is a value and a list. So a list is a value and a list until you reach a nil, right, at the very end. Your tree, right, the other data structure might be a node that has 2 other trees, like a binary tree, for example, or a leaf, which is your final value. But those are data structures, but you have your business report or some file system. Think of a file system. Element of the file system is either a folder that holds some other elements of the file system, or it's a file, which is a leaf. So those are all structures that are defined inductively. And you would probably find them in your project if you look for them. So for this presentation, let me show you like a simple example, because like the examples are simple because the idea is a little bit complex. So expression. Expression is a recursive data structure. So if I have this expression over here, I can represent it as this. I can represent this in code. So oh shit, sorry for that. Go away. All right. So so we have a sum of square of 10, and we sum it with a multiplication of 20 and a half and 14 and a half. If I want to square that whole expression, I would just wrap it up in a square, and yeah. So this is my representation. Is it something you guys understand? Like this is like a simple example, hopefully. You can think of it also as a tree, right? This is exactly what it is. The square is our root, and then we have our sum and the multiplication and all that, and our values will be our leaves within our structure. So now, this is how we would represent this in Haskell. And Haskell is a pretty nice language because basically everything I just said a moment ago is in the code base. In Scala, it looks a little bit more awful. But the cool thing about Scala is that we can actually color our syntax, and this is the thing I will be using throughout this whole presentation. So everything which is in gray, think of it as a boilerplate. Things in color are kind of more important here. So we have our expression, and that expression can be a sum, for example, where sum takes two expressions, xp1 and xp2. And so this is like one of those elements in our data structure. And we have two leaves, int value and decimal value, which are also expressions, and it actually holds the value. That makes sense? Yes? Thumbs up? Thumbs down? Thumbs up. Awesome. So now we could actually write a function. If we want to write a function evaluate, which for a given expression will actually evaluate it, the easiest implementation that you could think of is implementation that use recursion, right? So we would say, well, if it's an int value, give me that value and convert that to double. If it's a decimal value, just give that value. If it's a sum, for example, well, then before you sum those things together, first call recursively the xp1, and then call recursively xp2. And once you have those values, sum them together. So if you look at this example, you would actually see that there are two things happening in this method. There is our business logic, which is, well, evaluating the expression, but there's a lot of code that is responsible for traversing this data structure, from going from the root to the leaves and then going back. Is that an issue? Well, depends how much you are prepared to live with a boilerplate, right? If you come from Java, like me, it's something you do for a living. There's boilerplate everywhere. But so it kind of depends if that hurts your RCS or no. But you will see there are other methods, like for example, make string, which takes an expression and gives a string representation of that expression. And this kind of looks familiar, right? The stuff responsible for traversing the data structure is exactly the same. It's the only difference is what we do with those values, what we do once we actually have that value and we add them together. Like for example, we create a string here. So it kind of seems like we're doing the same thing all over again. But again, if you don't mind, yeah, this wouldn't be an issue. The issue is here. I might have a function which I would call optimize. An idea about optimize is a function that takes an expression and gives me expression back. The difference is that new expression I will get as a return value is optimized expression. And what I mean by optimize, it means that if I see multiplication where two things are multiplicated and they are exactly the same thing, I should just say that value squared. Why that's optimized? Well, think of it if I want to evaluate that expression which isn't optimized would be, well, evaluate the left side, go back, have some value, let's say 10, do exactly the same here on the right-hand side, 10, and then multiply it together. With optimized version, just go once 10 and then square it, right? You don't have to go the other branch. So it's kind of nice. So why the issue? Well, the problem is this first line is exactly what I just explained a moment ago, right? Saying if expression 1, expression 2 are equal, then we want to just say square expression 1, and we still have to traverse that down to optimize anything underneath that expression. The problem is we are not done, because in our lambda we just dealt with multiply where expression 1 equals expression 2. Now we need to deal with other elements of our algebra here, right? So all this other stuff that just appeared to be here, it's simply to traverse that structure. It's not doing anything, okay? It's just traversing the structure because it has to go through each of the elements of that structure just to go down, reach the leaves, and then go back to give you the final value. So this is a simple example where expression has like, what, 6 elements. Think of a little bit more complex recursive structure, and you can imagine the hell of functions you have to deal with. But that's not the only issue. The thing about functional programming is that people from Haskell will tell you from Scala that, oh, if my code compiles, it works, right? Well, does it? Not really. Think of a situation where, for example, I will forget to call optimize here on multiply. Will this code compile? Yes. Will it be correct code? No, because it will not traverse the structure till the very end when I have elements of my structure have multiply. Think of another error that I might have. I might actually call optimize on leaves. This code will still compile. The compiler will be happy, will be like, yeah, great, it works, right? But if you run it, it will never terminate. because once it will reach a leaf, it will just loop for eternity. So that kind of sucks. And what we would like to have is ability to deal with it. So this is example how basically evaluation works in this example. So we have this multiply, right? We traverse to those xp1 and xp2, so we have sum, and then we reach leaf and the other leaf, and then we go back, and then we go to the left branch, and then we go to the leaf, and we traverse all the way down. We reach to the values which are in the leaves, and then we traverse back our structure. And regardless of what function that would be, either evaluate or make string or optimize or any other recursive function that you will see here, they all exactly do the same thing. They traverse the structure till the very end, they reach for the values, then they go back, they fold up, they call some business logic on those values and until they reach the root, and then you're given the value. So the question would be, since this is exactly the same thing for every function that I write for this data structure, could I have some kind of machinery that would do that thing for me, right? It would just do the traversal through the structure, and the only thing I have to provide is this function that will take already the elements that I need and combine them together, and it would just go up to root and give me the final value. That would be cool, right? No? Hopefully. But the problem is that so what I want to write here is I want to write a function that would take an expression and give me the double, exactly the same function, but I don't want to deal with recursion. I want to have multiply where the elements of the multiplies are not expressions. What I want to have here is a double. I want to write a function that I don't have to deal with recursion. Recursion is done for me. It will reach the leaves, it will go back, while traversing back to the root, it will call my function here, so my function shouldn't really deal with expressions anymore. If I'm evaluating, it should deal with doubles. If I'm calling make string, the multiply should have string, so xp1 and xp2 should be string. If I'm dealing with doubles, it should be double, because somebody else is doing recursion for me. And this is kind of a trouble here, because this is how our expression was defined. Multiply or sum holds expression, nothing else. So how can I write my function that will deal with those scenarios that here can be different things? Well, the only way that we can do that is when we make this construct a little bit more generic. So we will say right now that expression is parameterized by some a, whatever a. So now, for example, your sum is not, it used to be xp1, xp2 used to be expressions, now it's some a, whatever a that is. It might be a string, it might be a double, it might be a user, whatever. We just made it a little bit, this structure, we made it a little bit more generic. We lost the recursion here, right? Because it used to be recursive by definition, and now it isn't. Now it can be just integer, or string, or double, or whatever. And just a reminder, we did that because at the very end, we want to write this function that will deal with expression of any type. Expression, so like multiplication that has two doubles, or multiplication that has two strings. This is why we're doing this. But now, once we've done that, we have a problem. Let's say you want to represent, because we introduced that expression to represent expressions. So here you have a simple expression, which is this example on the left-hand side is expression done in the previous simplified version of expression. So we just said sum of integer value 10 and integer value 5. Now, if we want to represent right now this recursive structure with our a little bit more generic representation, well, how can we do that? It used to be that sum had expressions, right, in it. Now it can be anything. So what can I do? Could that a here, that a, could be just expression? Would that work? It kind of does, and not in the same time. And let me show you how. So let's go from leaves. Leaves are pretty cool, because check this out. Int value is parameterized by a, right? But it doesn't use a, really. You can have int value of string, of user, of unit, of whatever. It doesn't really matter because nobody is using a here. Here just int value holds int, and decimal value just holds double. So I could say, so just to clarify, the thing I want to do here is I still need the ability to represent something which is recursive, like an expression, with my new definition. And I'm just trying to compiler to work with my new definition, because I made it a little bit more generic, a little bit more complicated, and I need to represent something like on the left-hand side. I need to represent it right now with my new definition, and I'm wondering if that's even possible right now. So what I can do with int values, it's actually quite easy, because I can say int value can be parameterized by anything, right? By unit. Doesn't really matter. Compiler will be happy because that a is basically ignored. The problem is, what about sum? What goes here? Well, let's try to think about it. If this thing is int value of unit is basically expression of unit, right? And this is expression of unit, then look at sum definition. If that was expression of unit, and this is expression of unit, then sum is parameterized by what? Expression of unit, exactly, and that's what it is. Awesome. So now, if sum is parameterized by expression of unit, and sum itself an expression, then our final expression is expression of unit. If this looks ridiculous, check the other example. So we can actually, this is a little more complex. So the complexity here grows in a way that the structure has now 3 levels instead of 2. And we can do exactly the same thing that we did before. So we ignore the leaves because they don't matter. Can be unit, can be string, can be whatever. Then sum is expression of unit, and decimal value also has to be expression of unit. So divide is expression of unit. So your final thing is expression of unit, which, as I said, still compiles. And it kind of, if you come from the Java world, as I said, your brain is already adjusting to deal with boilerplate. Like after a while, it could just deal with it, right? I just don't see it. So we could say, yeah, it sucks, but it compiles. Like, let's deal with that. Well, not really, because those 2 examples were expressions that were just defined by us on compile time. But let's think of an example here where I have an expression that comes from some method. So let's say I have a function that takes a string and parse it and gives me an expression, right? It's like the input would be a string, the from will be parse, and I'll just parse the string that gives me the expression. How could I represent this on my new generic form of expression? Well, we no longer know how many levels of it, because we don't know on compile time what kind of structure we're going to get, how many levels of complexity we have. So we basically would have something like expression forever. So you have now recursion of type level. That obviously will not compile, right? So it kind of sucks. Can we do something about it? As you guys remember from my previous talk, because we're going to introduce something which is called a fixed point data type, which might sound a little bit ridiculous and weird. And so again, I had this a picture of a kitty for your brain to relax. But however, we don't have time for your brain to relax, so you have to deal with it. There are many fixed point data types, and the ones I'll be showing is the simplest one, which is called fix. But a spoiler alert, if somebody is interested, free monad is also a fixed point data type. But don't worry about it. It's like something for maybe another talk some other day. Fix is the simplest one, but your brain might hurt if you see it for the first time. But I will help you out to deal with that pressure in your brain. So let's try to reason about fix for a minute, because it already looks ridiculous, right? Crap. What fix really is a wrapper. It wraps some value for you. You see, it's a class that takes something in constructor and just wraps over that thing, right? So far, so good? This simple. So let's try to figure out what it actually wraps. A spoiler alert, in our example, that f is our expression, if somebody's trying to look for a correspondence with our example. So that f will be our expression. All right, so we're saying that our fixed class is parameterized by f. Some f that also has a whole, which means it's a parameterized. It cannot be string, all right, or integer. It has to be something that is also parameterized, like our expression, which is parameterized type. All right, so now we will wrap something of that value f. Okay, so far so good. But could it be any f? Could I wrap expression of int? No, because I'm constraining here, I'm saying not really any f. Not really any f. Only f that is parameterized by fix of f. And now, we have like 20 minutes. So if this is kind of confusing, stay with me. If it doesn't compile in your head just yet, the slides are online, and I promise you it will eventually. But for now, bear with me and just think that it works, okay? Let's just assume that it compiles. It does, but if it's kind of hard to comprehend right now, I promise you it actually works. So let's see this in an example, because I think it actually will be easier to understand this with an example. So let's go back to that our simple example where we had this expression of unit. So what I want to do is I want to wrap every expression in this data structure with fix. Since fix will be wrapping that f, I just want to wrap every expression with that fix. And let's see what it will give us. So if I wrap int values with fix, then my integer has to be, so int value has to be parameterized by fix of expression, right? If I'm parameterizing something by fix and I'm parameterizing this, right? Then this thingy has to be parameterized by fix of expression. And as you guys remember, the int values just ignore the a here because they don't really care about a. All right, so if that works, let's wrap sum. So sum is right now fix of expression. So now let's wrap sum. Wrapping sum within fix will eventually tell us that we have a type of fix of expression. So what it's actually doing is it's catting. It just cats those x sequence into the first exp. And the type signatures kind of allow you to do that. As I said, if it's just too hard to comprehend on the first time, just try to go with the flow and kind of imagine that it works. Second expression, which was a little bit more complex, we'll do exactly the same thing. We'll start wrapping those expressions from the leaves, from the values, and we'll just go up to the root. So one more time, we wrap over that fix. So now we have a fix and parameterized by fix of expression, fix of expression, fix of expression, fix of expression, fix of expression. And Scala has this nice feature. It kind of from time to time can infer types for you. So here it will actually it will work. So we can pretty much delete this part. This part is needed by compiler, but if we skip it, compiler will be still happy. So if you look at it right now, it almost looked like something that we had previously before, right? It only had this fix at the very beginning. But beside that, we have ability to represent any recursive data structure with our expression that was generic. So, and if you remember the last example where we have this expression that comes from some method and we don't know it on compile time what kind of expression it is, fix will fix that for us, meaning we can just say we get a fix of expression. Now the question would be, yeah, but I don't want to have a fix of expression. What I want to have is expression. How can I get expression from fix of an expression? Anyone? How can I go from fix of expression to expression? Check the type signature. How can I go from fx of f to f? I can just call unfix. I can just say expression.unfix, and this will give me the expression. So what we did right now is what I would say every government is doing. So we kind of introduced a problem, so then we could solve it after 30 minutes. But we introduced, so what was the problem? We had a pretty much very simple data structure expression, which was recursive in its nature. And we could create recursive things, like recursive expression. We could define expression. Then we made this simple data structure, we made it generic, which didn't allow us to actually build recursive things anymore. And we fixed this with fixed type. But we provide that generic type for a reason. Remember that the idea was that we will have eventually at some point a function evaluate that will take an expression and go to double, and those expressions will be no longer expressions, it can be anything, a double or a string or something. So now we can actually do it. We're getting there. We're almost done. So there are like two things we need. We need to have ability to traverse our data structure. Because as I said, we want to have this machinery that will traverse the data structure for us, we'll go to the leaves, go back, and we'll call our function while traversing back, right? But that machinery has absolutely no idea about the data structure that we may have. Here we are using expression, but it can be your business report. It can be any data structure that you could think of. So we need to help him with traversing. And one of those machineries, those recursion schemes, one I'll be talking about is something which is called catamorphism. And you might be thinking, oh, this is something horrible, difficult from category theory. It has absolutely nothing to do with category theory. It's Eric Myers. You remember the bald guy with colorful t-shirts, LSD and heroin and all that stuff? He made a paper where they introduced those recursion schemes, and every recursion scheme gets a weird name. So catamorphism is basically fold R. It's fold R. But they call it catamorphism for whatever reason, and also in the paper they use operator for represents a catamorphism, and that operator looks like a banana. And that's official academic paper from 1995. But whenever you see catamorphism, think of fold that you normally use on lists. This is exactly what it is, because this is what we've been doing with those methods, evaluate and make string and all that. This was basically folding, right? We took an expression and we fold it to double, or we took an expression and we fold that to a string. So I'll have to skip like, so we need to have ability to traverse that structure, and we use that with functor. Now the question is, who is not familiar with functor? Everybody is. All right, if I ask definition, random person, you will be able to explain it? Yes? All right, I hope you guys do, because I had a functor 101. But basically, for people who don't know functor is, and they just don't want to raise their hand because, yeah, whatever, functor is just a trait, like this oversimplified definition here, is just a trait which we have to implement. And that trait has a simple method, which is called map. So what we're saying here is we need to provide implementation for this method map. And that method is supposed to, like, given I have expression of type parameterized by A, and also I have a function that will go from A to B, it should give us the expression of B. So let's say I have an expression of parameterized by string, and I have a function that goes from string to double. When I call map on it with those parameters, it will just give me expression of double. And we can implement this function pretty easily. And I'm just saying I have 10 minutes, so kind of stay with me. It works. It compiles. It just basically, it kind of looks like just traversing using explicit recursion, right? It almost looks similar. But yeah, it compiles. The nice things about functors is that type classes, so the functor is a type class, they have laws. You can actually take this implementation into Scala Z and run tests on it, and it will check whether all laws apply, yes or no, so you are 100% sure whether this is correct implementation or not. once we have this, so once we have a functor, so once we gave that machinery, which we're going to see in a minute, that machinery, the catamorphism, we will going to give him the functor. That's one thing that he needs. So this ability to traverse our structures, like give him some hints how to traverse that structure. The second thing that we need is our function, that finally we are reaching this function that I promised that we will implement at the beginning of this talk. So to make things a little bit complicated, we will not call it our function, we will call it by name. That name is F-algebra. Now, this comes from category theory, and that's a scary name, right? But it really isn't, because what F-algebra is basically a function. So algebra FA is nothing else than just a function that goes from FA to A. So to put that in an example, let's try to write right now our evaluate function. It's going to be an algebra expression to double. So this, as I said, this is just a function that goes from expression of double to double. And now we just removed recursion totally from our definition, right? We only deal with business logic, quote unquote, only deal with what it means to evaluate expression. Because if I have sum here, the A1 and A2, they're going to be doubles, right? And multiply those two is going to be just doubles. Same goes for make string, which is an algebra from expression of string to string. So now I'm only telling what it means to represent given expression as a string. I no longer have to do any traversal, any recursion whatsoever. So if I don't do it, who does it, right? I said we will have that machinery. So all the recursion schemes, I'm only showing single recursion scheme, which is called catamorphism, the fault, right? All that is implemented in this project called Matroska, which is open sourced and you can use it. It goes like this. You guys remember, we need to have that algebra, so we need to have this function that goes from here from expression of double to double. We need to have that functor that we've seen before implemented for expression. This is some example of an expression. We divide and we sum some numbers together. And then we will just call expression kata from catamorphism and evaluate, and works. So now we have, like, you might be thinking, this is like super complex, some additional complexity and unnecessary complexity within my project. But think about it for a minute. You don't have recursion anymore. How complex are your projects because of recursion? I mean, it doesn't mean recursion disappears. It's still in your project, right? But it's hidden. And there's like, remember that example with, so this is make string, and it's exactly the same thing. So I have this algebra example I call make string, and it gives me string representation. But remember this optimize, the awfulness of this implementation? This is how the algebra will look right now. We completely remove recursion, but also what we remove is ability to make errors, like implement a function that will never terminate. And also, our definition is right now very concise. We only have things that we are interested in. We're only saying, listen, if it's a multiply of x a1 and fix a2, and a1 is equal to a2, then optimize it into square. Otherwise, give me what I had before. That's it. I'm happy. So we lose all that craziness that we would have with when we traverse recursion, all those errors that we might have. And to be honest, and this is an example that it actually works, so just believe me, it works. So I have 6 minutes, so I will not go like deeply into all the examples that I have because it's not impossible to be done in 6 minutes. But what I showed you right now is that's the problem of explaining recursion schemes, because I just show you the tip of the iceberg, which is the foundation to understand all other crazy stuff, which are actually pretty cool. And they give you the power. Because this is something like what you're seeing right now would be like, well, I don't know. I would just prefer calling like recursive like my functions and maybe write some tests and it will work anyway. But this is just the tip of the iceberg, and I will try to show you like cool other stuff within 6 minutes. I don't know if it's doable. Maybe it's doable. Let's try it out. So catamorphism is one of the recursion schemes. There are other recursion schemes that are completely zoo of recursion schemes, which were researched over the years. And I will show you very quickly 2 of them. So anamorphism is something reverse to catamorphism. So when catamorphisms takes your structure like expression and give you a value like double, anamorphism is the other way around. It takes you a double and gives you an expression. So it takes a value and explodes you the expression. So example would be, think of, let's say I have some value and I want to represent that as an expression where I multiply 2's and some odd number. So I give you an integer, and back you will give me an expression that represents that integer. So this is the other way around. But this time, instead of implementing algebra, you guys remember algebra went from expression to value, we have to implement its dual called algebra. So it's the other way around. It takes a value and gives you an expression. So very quickly, the co-algebra that we would write would look like this. So listen, if n is divisible by 2 and it's not 2, then just return multiply 2 and divided by 2. If anything else, give me that integer value. So now we could call like 12 anamorphism with that co-algebra, and that would just give us the expression. It would explode the representation of that value for us. You might be wondering would I need it, yes or no. I could talk about it, but maybe after, during the break. What is important, because I'm showing you anamorphism to actually show you hilarmorphism. So hilarmorphism is another recursion scheme. It's basically what it's doing. It's first, it will take as an argument 2 things. It will take a co-algebra and algebra, and it will take a value, and it will first call anamorphism. So it takes your value, explode that into some kind of structure, and then take catamorphism and then fold that structure back to a value. Think how you would implement factorial, for example. This is a stupid idea, but a stupid example of it actually works. Factorial, right? So you take 5 and you explode that into expression. So that would be 1 multiplied by 2 multiplied by 3 multiplied by 4 multiplied by 5. And then you have evaluate that will just wrap it into a value, right? You could just go like this and that. And that is doable, and you can do it with what we have already. But hilarmorphism just does it for you. So you might be saying, what for? Well, if you think about it, anamorphism will take your value, and it will first explode your structure, and then you will call catamorphism, while catamorphism has to go through your structure to the very leaves, and then it goes back to give you a value. What hilarmorphism is doing, it's doing the same thing, but in parallel. While anamorphism is exploding your structure, catamorphism is already wrapping it up. So they go in parallel. This one thing is just exploding this, but at the same time in parallel, catamorphism is just folding it together into final solution. So they go in parallel together, and then catamorphism has to only go back. So it's like it's just twice as fast. And just to give you an example why that might, okay, so just let's skip it. 2 minutes. I work with compilers in my current project, and you know Scala is slow, right? Why is Scala slow? One of the reasons, there are many reasons, but one of the reasons might be that the fact that the compiler actually has phases, right? It doesn't go from your Scala code directly to bytecode, to assembly, right? It actually goes through some phases. So think of, for example, of a for comprehension. For comprehension as basically a sugar for calling flat map at the very end, right? So you have a phase that will go from your source code from AST, and it will just desugar the for comprehension for you. And then you have one more time AST, you have the source code, and then you have another phase that will do some other stuff, and so on and so forth. And this is something in compiler which is called multipassing, which is nice. Why? Because, well, you divide your very complex problem of compiling Scala code, which is a complex thing, into small little things that you can reason about, like what does it mean to desugar for comprehension? What does it mean to do some other stuff when we're compiling Scala code? so they can reason about it separately. You can test it separately and it all works. And your just final compilation will just go through all those phases. Why is that an issue? Well, the issue is because you have to traverse your tree, that representation of your Scala code, multiple times. You have to traverse it once to sugar the for comprehension. You have to traverse a second time, and the third, and the fourth, and so on. So there's another way to write compilers, which is called monolith. And a monolith is a pretty simple idea. I have my code, my AST, and I just give you an assembly. Everything is one single place, like a huge function that does everything, which is fast, but maintainability is horrible. It's just because you have everything in a single place. Try to imagine that, right? So the cool thing about recursion schemes is that they give us one more time everything what we kind of strive for when we do functional programming. They give us composability. You can compose recursion schemes. So now, if we are writing a compiler, we might have a first phase that will be doing something, and that's implemented as a recursion scheme. Let's say Amorphism, that goes from expression to expression. I have another phase that goes from expression to expression, and then another one, and yet another one. And I can reason about them separately, right? The same as we could do with multipassing. But the difference is, those little things, they compose. So my final compilation that goes from expression to assembly, whatever that assembly will be, is just take recursion scheme 1, compose with recursion scheme 2, compose with recursion scheme 3. That is being done on compile time. And I get the final recursion scheme that acts like that monolith. It's super fast. Even though I implemented those separate recursion schemes separately. I can test them, I can reason about them. And there are all other tools, cool stuff that you can do with recursion schemes. And in our project, it just really works. And if that, one more time, is exactly the same thing as with my talk about free. I know it's kind of overwhelming sometimes. I mean, the first week I've been working for something like that, I was just banging my head over the wall. But eventually, it clicks. And when it does, the new world opens up in front of your eyes. Because you can really do engineering. You can really reason about your code. What I encourage you guys to do as a homework is basically to try to think of a new recursive data structure that you have in your project and try to take any function that is recursive within your project and try to find a recursion scheme and implement that using recursion scheme and see if that works for you. I guarantee it should. Thank you very much, guys.